Maximum likelihood methods, they try to find the tree that maximizes the likelihood of the given genetic data while considers all possible trees. And what it does is, by using a tree model for nucleotide substitutions, it tries to find the most likely tree out of all trees in a given data set. So this approach can be presented in these points. So the bases are considered independent, and log likelihood of having these bases are computed for a given topology by using a particular probability model, and this log likelihood is added for all sites, and the sum of the log likelihoods is maximized to estimate the branch lengths of the tree. Remember, we are playing with small numbers, so when we talk about probabilities, our numbers are really small, and when we multiply them, the products becomes further small. So that's why we take log likelihoods, or we take the log values and then we add up those values. So this procedure is repeated for all possible topologies, and the topology or the tree shape or structure that shows the highest likelihood is chosen as a final tree. So this approach is a statistical approach where probabilities are considered for each nucleotide substitutions in a set of aligned sequences. And this approach has, there was some contribution of some scientists, so they produced that the method of sequence alignments based on models. So these scientists, they came up with a model, and then they correlate that model with these probabilities. So the model predicts the manner in which DNA sequences change during the evolution. And if we look into these different changes in nucleotides, we see that nucleotides can change into the same type. For example, where we can see purines can change into the purines, we show them, and same way pyrimidines can change into the pyrimidines. Remember, AG are purines, C and T are pyrimidines. These green edges represent transitions where the change is within the same group, whereas the red edges represent traversions where the change is across the group from purine to pyrimidine and vice versa. So these statistical models, they take into account what type of these mutations are there in those nucleotides. If they are transitions, we have different probabilities, and traversions have different probabilities. So we can come up with a probabilistic model, and we incorporate that model into our phylogenetic predictions. So here in this example, for example, you are taking in each individual position. You are not taking the whole column, so you are aligning C with T, and then you are aligning C with G, and same way you are aligning T with G. So in this case, you can look into which one is the most likely. So the sequence with C and T are more closely related to each other than they are to the sequence with G. So where we see those transitions, and the most likely scenario is that there are more transitions than traversions. So those sequences where we have C and T, they are kind of more correlated one another. So in this way, we are incorporating the probabilities related to those transitions and traversions. So here is how we can elaborate while using the example which is there in your book, Mount's book. So you come up with 4 different sequences, A, B, C, and D. We align them, and we can come up with an unrooted phylogenetic tree for these sequences. We can come up with something like this. Then we incorporate the roots in those phylogenetic trees, and we can come up with different likelihoods or different scenarios. So for example, there is one variant of these aligned sequences where we have A and B, C and D. We are right now considering a column where in A we had a T, in B we had a T, and then we have A and G in the C and D. So we can come up with their hypothetical ancestors, which are represented here as 1 and 2, and the common ancestor to this whole tree is represented as 0. Same way we can come up with different likelihoods. So this hypothetical ancestor, starting with that at 0, its likelihood is L0, and then we can have other likelihoods. So we can have we can go from this ancestor towards left, where we can have the likelihood L1, We have L2. If we go towards right, same way we have L3, 4, 5 and 6. So in this way total we have 6 likelihoods, or 6 changes are moving into 6 different dimensions on those tree. In the second variant, where we can have their ancestors, common ancestor is given a letter T, so again we can come up with its likelihoods. So we can come up with different trees with different arrangements, and we can come up with their likelihoods. So here we put this common ancestor as G. So there is another variant of this tree, and it also has L1 through L6, 6 likelihoods which are present in this tree. Likelihood L of the tree can be calculated as given by this relation. L of tree is equal to L of tree 1 through, and adding with tree 2, and it goes till tree 64. Since we have 3 interior nodes, 0, 1 and 2, and at any node in these interior nodes we can have any one of A, T, G or C. So total we have 4 into 4 into 4, 64 possible base assignments, and in this way we can come up with 64 different trees. How can we calculate the likelihood of tree 1? So that is given by all likelihoods which are present in that tree. So product of all of them, we can take their product, or we can use a log scale. In that case, if we take the log values, we need to add up these numbers. L0 is the likelihood of starting with any nucleotides, so we can start with any one of A, T, G or C. So it is 1 by 4, 0.25, and the likelihoods for transitions is 2 into 10 power minus 6, whereas for transvariance it's 10 power minus 6. So while using these numbers, we can calculate the likelihoods of any trees, tree 1 and up till we can go till tree 64, and either we take their logs and add them, or we simply multiply them. So in that case, we can come up with the overall likelihood of the whole tree. So we see in this section that this maximum likelihood approach is a probabilistic model kind of a thing, where we can come up with the likelihood of one of the trees, which is the product of the likelihoods of its individual components, and same way we can get the likelihoods of all of the trees involved, and we can use those numbers to calculate the most likely tree from the given set of sequences.